What's going on, everybody? Noble here with you guys to discuss quality right of this video. Now, I do also this video capture your display just the way that I've. After that, you're gonna go ahead and scroll all the way down and jump into graphics. And once you're in program, this is the actual application. You actually get a black screen is because right here it says power saving GPU will give us, and everything is working. We've got fix mark down below after, and that's the way that you using XSplit to make this video possible. So should be working just the way it is. You guys can see everything is working. We've got OBS.
Success doesn't have to mean getting the corner office. It isn't always climbing the corporate ladder.
Hello, hello, hello.
Hello, hello,
Yeah,
hello, sir. Good afternoon.
yeah. Good afternoon.
Good afternoon, sir. Actually, our participants will be joining shortly. Few of them have joined.
Okay,
So, yeah, I request all the participants to join. Sir is waiting. So, let us welcome our post launch session speaker. He is Dr. Lalit Singh. He is working in Bhabha Atomic Research Center as a scientist. So we are very much fortunate to have him with us. So he will speak on the topic that already been shared to your group, research scope in nuclear energy. So I welcome again, sir. So it's over to you, sir. Thank you.
thank you. So to start with, let me share my slides. Are slides visible? Hello, are slides visible?
Yes, sir.
Yeah, yeah. Thank you. So I'll be talking on research scope in nuclear energy, and which is also a green energy. So, and we'll see because nuclear energy is a very emerging field, and like in especially in India or in Asia, several nuclear power plants are under construction also, and hence there is a lot of scope in this nuclear energy, and it is basically a multidisciplinary area. So let us see what and I think the audience would be of mixed type, so it would be useful for all the audience. So first, let us try to understand what is a nuclear reactor, from where the nuclear energy we get the nuclear energy. So a nuclear reactor is basically it is a device, and that is designed to maintain a chain reaction. So what happened we know the heavy nuclei atoms, they do have a tendency by splitting, they do spontaneous
Good afternoon, sir.
Good afternoon.
Hi, good afternoon, sir. Hello, actually, sir. Please.
Okay. Good afternoon, sir. Can you hear me, sir?
Yes, I can, Dr. Pritam. How are you, sir?
Very fine, sir. How are you, sir?
Good. Nice to be with you. Although I wish I could be with you.
Okay. So, shall we start, sir?
Yes, if that's okay.
Okay, sir. Let me give some introduction and we can start after that.
That's okay.
Okay. Respected coordinators of the webinar, Dr. Mujib Dev and Dr. Sabnipal once again. Our director, sir, who is present here with us and who has been a constant source of support. The participants from all over the country. Ladies and gentlemen, and Dr. Richard Bernard, who has been very kind who has given the council very kind enough to be present here among us. Of course, we could have, if we had chance, could have invited you and come and see us physically, but situation has not permitted to call you physically. But anyway, we are able to see you virtually. That's a privilege for us. Our Department of Mechanical Engineering started its journey in the year 1965 in Aswell Tripura Engineering College with only one student in the undergraduate program. We started with only one student in undergraduate program. Now the college has been connected in the year 2006. Now we have an intake of more than 110 in BTech program, 70 in postgraduate program, and 60 scholars are pursuing PhD at present. We have 27 faculty members in the department. The curriculum is taught by distinguished faculty members combining academic excellence and real world experience with dedication and commitment. Now our speaker, I don't think we need any introduction to him. He is expert in his own field, and we expect everyone to be present and gather whatever necessary information from him, so that it becomes fruitful for everyone who will be attending the program. Sir, have you heard about Sir Richard? Have you heard about Rabindranath Tagore?
Sorry, I didn't quite catch that.
Have you heard of Rabindranath Tagore?
No, I haven't. No.
No, okay. He's the first Nobel laureate of Asia in literature. And he has visited several times in his lifetime. Our several times, and he had a very the national anthem of Bangladesh and India is written by him. So he has visited us several times. So if you have a chance next time, kindly visit our, if you have an opportunity, if you do invite you, then kindly visit NIT Agartala and see for yourself. And it is one of the underrated NITs. We have got so many facilities here, which is much better than some IITs also. But still, as it is somewhere locational problem, that's why it's not getting that much of coverage or that much of advertisement from others. Anyway, so with this brief introduction, I welcome you all in the webinar. And Sabnik, you can take over and we can just start the program. Thank you. All.
Thank you.
Shabdik.
Yes, sir. You can start.
What about director sir wants to say something? Shabnik?
Yes, sir.
Have you talked to director sir?
No, sir.
Okay, sir. We can just start. Thank you.
Thank you.
So thank you, sir. I welcome you, sir. So, sir will deliver a lecture on life cycle assessment of alternating technologies for converting MSW. So it's municipal solid waste into electricity and chemicals. So, sir, please over to you now.
Thank you very much. and thank you very much for this opportunity. I hope you can see that slide now. Should it be coming? Can you see the slides okay?
Yeah, we can see the slides. No problem.
Right, fantastic. So thank you very much for this invitation, and also thank you very much for the organisers, and also I'd like to thank all distinguished guests from faculty and also the students who are here, and it's very nice to be with you, joining you in your afternoon. It's morning here in the United Kingdom. I would love the opportunity to come and visit you at some point. I'm very fond of the northeast of India. I have had the opportunity to visit Mizoram State and Nagaland, as well as Assam in the past. So, another opportunity, I would very like to come and join you at some point. Okay. Let me find the... Okay, so my topic, which I'm going to talk about today, then, as I said, is about life cycle assessment approaches for converting municipal solid waste into electricity and chemicals. And I'm going to start off very briefly, which is a very short couple of slides about where I'm from. This is Loughborough University. It's very much in the middle of the United Kingdom. As you can see here, we're about an hour and 10 minutes from London by train. We have other cities of Birmingham and Leicester nearby. And it's a very, I think also a very green campus where we work. Yes, it's very, I like about the North of India is it's so green. And so this is an aerial shot of our campus. There's very famous for sport at Loughborough. So hence a lot of sports pitches you can see there, cricket pitches, running tracks. And I work over in this building in the far corner. It's not a very exciting building. And this is where Crest is based, and this is where I work. And I work at the Centre for Renewable Energy Systems Technology. And we're going to take research and teaching into low carbon technologies. And we have a team of about 15 academics at this moment in time, plus researchers and PhD students, makes about 60 people in total. And we focus on a number of areas of research in terms of materials, solar materials, devices, photovoltaic, wind energy. I concentrate a lot of my research in renewable energy for development. We do energy storage, networks, and also multi-scale energy system. So this is largely technologically based. We do sometimes reach out into areas of social sciences and economics, but largely focus on technology. And I'll just show a couple of slides to illustrate some of the research that I've been involved with in the past. So I've worked on projects in India on biogas, and there's a couple of pictures here of different facilities. We had a project which was coordinated with Agartala and Tesco University, and I think also Chennai, where we were looking at installing biogas systems in villages. I've also worked a lot in what we call mini grids. So on the right-hand side here, we've got this is Borneo, this is the Malaysia, Sarawak region, Malaysia, and this is about school microgrids project. In the middle, we have a gasification project work, and this is actually a facility in Ecuador, where I was working with the Ecuadorian Renewable Energy Centre to look at ways of modelling municipal solid waste to produce syngas, and what are the challenges of using municipal solid waste. And also in the bottom right-hand corner here, we've got another hybrid mini-grid. This is in Malawi, and again, it's got the idea about mini-grids for energy for development. So what's the motivation behind this particular topic about municipal solid waste and converting it into electricity? Well, the challenges we face are that we still have a growing population, and our economic models seem to be geared towards making things cheap, but not worrying about what happens to the products we then discard afterwards. So that's ultimately, one of the problems we're facing is we're getting more people, and generally people's livelihoods are improving. Sometimes we may not feel it, but generally, people's livelihoods are getting better. People want more things. They like to have a better standard of living. But unfortunately, we're throwing stuff away. And even with our best efforts with recycling, we're still producing large amounts of waste. And this is set to grow and into the future, very near to 2025 now. And this is causing all sorts of problems, beyond just the amount of waste which is being produced, but there's plastics which are getting into our bodies, into the oceans. Our continued use of energy is causing global warming, and this is leading to other wider issues. And it's all being driven by the sort of economic models which we have, which is about making stuff. And we have to have jobs, but we have to think, how can we do things more sustainably so that we don't end up with the worst consequences of global warming? And one way potentially to do that is to try to think of converting wastes into useful resources for us. Now, there's lots of arguments about recycling, so we need to do a lot of recycling as well, but we need to ensure that we're trying to convert our waste into useful products, and not dumping it in the ground or sending out into the oceans. So, municipal solid waste. And so what is municipal solid waste? As the name says, it's basically everything which people will be throwing away. And so made up of a mixture of materials as illustrated in the slide here. Organic matter present, but also things where we can recover materials as well, such as plastics, glass, cans, computer, electronics as well, to actually recover some of these resources. But we're producing this material and we have to do something with it. And so historically, what we tend to do is to put things into landfill sites, and unfortunately it's very unstable, and it also leads to a lot of leaching of chemicals into the environment, and also it produces methane, which is much stronger, potent global warming gas. So what we're doing in the UK is to move away from landfilling wastes. There we go, okay. So we're moving away from the landfilling of wastes to making energy from this. So we're seeing a decrease in material in landfill, but more energy. But it's a very controversial topic because people are saying, why aren't we recycling more? But it just gets more challenging, more difficult to recycle materials. And even Germany, which is probably the most advanced in the world in terms of policies, is really struggling to cope with waste. And so ultimately, what we want to try to do is to get waste down to zero. It's still a struggle. So seeing over this low peak, we're seeing a reduction in the amount of material going to landfill, but it's not really reducing as rapidly as we would have hoped. So it's taking time. But UK is not the only country struggling with the problem of what to do with waste. And Europe is seeing a lot of countries producing use of landfills, making waste-to-energy facilities to deal with their waste problems. And so the UK has got 41 plants, probably a little bit more now. Sweden, which is a much lower population in the UK, 33 plants. Germany, you can see here, we see the numbers here. France, ways of trying to deal with waste. And so the Western countries in Europe are very much favouring waste to energy solutions and moving away from landfilling. Now the problem, of course, is that we can make we can just basically burn waste through combustion and produce electricity. But the purpose of this talk is to see, well, is that the right approach to other ways in which we could reduce waste, but also make other useful products from it? So the idea behind this topic for this lecture is to compare and analyse alternative technologies to valorise, convert municipal solid waste using a life cycle assessment approach. And this topic will cover a number of different routes to make waste into energy and also into chemicals. And so this flow diagram here illustrates the routes. Now, the main routes start off as combustion or gasification, but then from the gasification side, we produce a syngas, and this can then be used for a range of different alternative solutions, which we'll look at in a little bit more detail. I'm not going to spend a lot of time going into detail, given the time we have available, but these will give you a flavour of alternative approaches to dealing with waste. I'm also not going to look into the economics of this, but what we have with these particular technologies is that they are all solutions which are technologically achievable. So actually they are at a maturity level, a technology readiness level, which means that it could be deployed as commercial solutions rather than being demonstrated. So everything here I'm going to talk about has got to a stage where there are plants already in operation and could be scaled up. But the reason we tend to favour combustion route now is purely down to the economics. It's much cheaper and just burn stuff and then use electricity. But there are disadvantages in doing that, which I'll talk about a little bit more later on. Okay, so let's look at routes. So then we have solid waste. This is route 1, going through combustion to produce electricity. Then we have got the route of gasifying the waste to produce gas, which can then be combusted at another time and then to generate electricity. Then we have the idea to produce methanol, which can be used for transport fuels. We can also convert methanol into dimethyl ether. Dimethyl ether is another fuel, but it's very similar to diesel in its properties, so it can be used as a diesel substitute. Then we've got that can be by a methanol production or directly from the syngas. Then we have the idea to methanise the actual syngas just to methane gas. And then the last route is to take that syngas and use fuel cells and make electricity. So the idea behind this talk then is going to weigh advantages and disadvantages of these different routes. Right. So let's look then. So look at these different technologies, just to give you an idea of what they're like. Again, I'm not going into a lot of detail with them. So we start off then with the idea about just of combustion of wastes, and say this is the sort of the industry standard now. There are some gasification plants in the UK and Germany, but generally the route taken has been is just burn waste and produce electricity at the moment in time. So that's just a couple of pictures to go with this, just for illustration. So this is fine. But what it means is you need to use that electricity instantaneously, so it has to be there and has to be demand for electricity, and so that would then require you to be shifting other forms of power generation to ensure that you've got use of this electricity. And is fine because it's seen as a low cost solution. The next idea is then looking at gasification. And the idea behind gasification, as I'm sure you're aware, is to produce gas. And again, there are a whole range of chemical reactions which take place to produce gas, carbon monoxide, hydrogen, water, and methane. And that again has potential advantages because that gas can then be used at another time. So you can store the gas. It doesn't have to be used straight away. So it could be used for short-term storage. and then that could be used potentially at times of peak demand. And in the UK electricity network, the price of electricity varies. So during the peak times of the day, in the evenings, when people are cooking and that's just a big load, then the electricity price goes up. And then that's a good time to sell your electricity. So if you store gas from a gasification process for a few hours, you can then allow that to be used for generation by burning through gas engines to make electricity, which could be seen to be a profitable route. You also generate electricity, and you can also recover wastes from this as well. And just to thought out of interest, just to talk a little bit about another gasification opportunity, and this is a CID I visited a couple of years ago now in Assam State, which is a gasification plant for baking biscuits in Assam State, and it's a really great idea of making use of bamboo. Which is from here it goes the bamboo. It's quite a nice system because the factory themselves aren't involved directly. They have intermediaries who go out to the farmers and they collect bamboo, and then it's brought in and then it's gasified. So you do this big crane here which takes the bamboo up to the top of the gasifier, and it gets fed in to gasify here. So it's a very nice system for local farmers, provides some income. Every farm's got bamboo growing. It's a grass, so it's not you're not cutting down forests. And it can be gasified and produced for gas baking of the biscuits at the factory. I want to illustrate some of the extra issues with gasification to make it why it is seen to be not as economically attractive at this moment in time. And that is there's a lot required. So you have to clean up gas to remove particulates and tar. So you've got a whole range of scrubbing cleaning process required here. To make sure the gas is going to go into the factory and clean for combustion and biscuits. One of the challenges though with gasification is tar, and it is the $1 million question if we solve this route of that, producing tar in the first place. This would make gasification much more attractive. The tar itself, which is produced, does have a little bit of value to it. It is sold to local road builders, and they will use it to help maintain the roads. Not huge volumes being produced, but even after all the cleanup within from the outside of the factory, there's still some tar coming into the factory, which is trapped ensures that it doesn't contaminate any products. And they're really nice biscuits, must say. So that's just a little illustration. So then just briefly run through different approaches. So we have the methanol synthesis. So we have a reactor where the gas comes in. It goes through catalysts to mix it with water, and then it produces the gas as the outlet. Also generates some electricity as well. And the primary reason for this is methanol as a fuel. So that's sort of the driving force for this particular process. So the dimethyl ether production then. So again, this is a process of taking gas with methanol and actually produce dimethyl ether, and that's sort of outputs from producing diesel fuel, and also generating some electricity, and again making use of catalysts to do this. And we have solid fuel cells. So the syngas can then go into fuel cell and then generate electricity and produce quite a lot of electricity in this particular process. And the gas itself, after through fuel cell, will still have some unreacted gas, so some hydrogen still present, and this can then combusted and generate more electricity. So here we're not looking at chemical production, we're purely looking at electricity production. And then methanation, and in this process we take the syngas, it's heated, and then goes through another catalytic reactor to produce methane, and water is also being produced here. These are the sort of the main reactions which take place. So carbon dioxide and hydrogen, monoxide, hydrogen, methane, and water. So water being produced. But again, what we're wanting is methane gas. Any unreacted gas will then go to be combusted and produce electricity. So that was just a very short introduction to different routes for producing electricity and chemicals. So the next part of the talk we'll look at the methods to think about the life cycle assessment of these different routes. So life cycle assessment. So I don't know if people are familiar with this, but it's the way in which we are looking at the whole life cycle of a product or process and what its impacts are on the environment and also people. So we have a typical model to show a manufacturing process. So we start off with resources, which are then manufactured into the products, which then get distributed to consumers. And then at some point, when they break down or we want to replace them with the next best gimmick, the next gadget, which is much better than the last gadget, we then recycle these, or we may just throw them away as waste. And maybe then we'll get those resources back again. And this process life cycle has been around for nearly not quite half a century, but it started in the 1960s. Coca-Cola was the actually first company to ever undertake a life cycle assessment. And the reason why people do it is to, you'd like to think they're doing it for environmental, but it's largely about trying to save money on processes to cut out waste. So I think consideration for the environment was probably secondary. So people were really looking at how do they reduce their waste and help increase their profits, which is perfectly fine because it does then have the benefit of reducing the impacts on the environment. So if that's the rationale. And what has been developed has been a lot of research into coming up with a process, and we've now got an international standard, 14040. So it's the ISO standard for life cycle assessment. ISO 9000, maybe some of you've heard of, deals with management systems in businesses. There's also ISO 14000, which is about environmental management of businesses. And ISO 14040 looks at the life cycle assessment of the processes within the business. Now, it's divided into 4 sections, and so it's quite straightforward. And it starts off with the first section is, what's the purpose? Why are you undertaking a life cycle assessment? So it might be, you want to save money, or you might want to promote the environmental credentials of your organisation. Now, for life cycle assessment, you can cover every aspect of your business, from literally the resource extraction, or even potentially the machinery used to extract resources, right the way through to the end of the life cycle of a product. It tends to focus more around the manufacturing area, which is why it's illustrated here with red dotted line. So you actually define boundaries for your process. Okay, so this is your system. So we're going to concentrate on the manufacturing process. What goes on within the factory, because you may not be able to control what happens in terms of transport and distribution. So you don't necessarily know how your goods will be sent from one country to another. They may be, for example, flown, or they may go by ship at different things beyond control. And where you get your resources from, you may also be restricted. But it's not to say that you cannot do the whole process and look at, for example, recovery of materials and what happens to them afterwards. So you set a system boundary and then decide that. You also need to work out a thing called what's functional unit here. Now, a functional unit may relate to a certain amount of product you produce. So, for example, you may be per car or per 50 cars, or it may be, for example, how much resource coming into factory. So maybe, for example, 100 tons of plastic we will make so many products. And the reason to do this is, I hope you want to try to standardise what you're doing. You want to standardise your approaches, and that's why we have the functional unit. And when you have this, you then want to look at your what's termed the inventory analysis, and this is where we, define our inputs and outputs of our processes. So when you're manufacturing something, there'll be inputs and outputs to it. So there may be resources added at different stages as you make your product. And you want to also know, when you add that resource to a product, do you produce any waste from that, or and what happens to those? And so you do this, and I'll show you in a little bit. You have sort of a vertical route of your manufacturing process, and cutting across it will be the different stages where different materials will be added. So it could be, for example, the packaging at the end will be added. And what you then want to do is collect data on those resources and what's been used, and work out what is the environmental cost of those. That's the environmental burdens. And when you've done that, you then want to think about, okay, well, what are the impacts of this going to be? And you want to think about where these impacts are going to affect. So this then moves into the third stage, impact assessment, where you select the impact categories. Where does this resource, this thing I'm making, impact on the environment or on people? And then you try to estimate what those impacts actually mean. So and that's again quite a big piece of work. You maybe look at a whole range of different chemicals involved in that, but it's necessity to be done. And when you've done that, you then want to move into your the next stage, which is the interpretation of this. And this is where you want to identify what are the main impacts, because you can have thousands and thousands of impacts, but maybe just a few of them actually make any difference, are actually significant to the effects on the environment. And then you want to then evaluate what that actually means, okay? And so this is where we've got the decision-making process. So we've got the science of the process, then we need to then bring in the art of the process to actually make decisions about how you're going to change your operations or make your decisions as to what route would be better. So can you reduce the amount of waste, for example? And then, because that might be a cost implication, you might need to buy a new piece of machinery, or you might need to train your staff to work differently. And ultimately that would then lead to conclusions. If you're doing this, it does allow you to say, if you do get ISO 14040, you can stick it on your websites and on your lorries and on your literature as well. So it's a good thing to do. So if we want to then, that's an explanation about what life cycle assessment is. So now let's look at the topic again of waste to energy and chemicals. And so what we first need to do is work out what's our waste fraction, how much is of different wastes are present, because this is going to affect how much energy and chemicals will be getting reduced. So for the purpose of this activity, the functional unit is 1 ton or 1,000 kilograms of waste. And from that, we'll then be able to produce different amounts of electricity and chemicals. But we need to know what goes in first of all. So the idea here was to model what a typical waste would be, and then use that as a standard to allow us to then run through sort of the design and model of the 7 different routes. So this is an example here of waste in the UK. This is the sort of the average waste. It'll be different in different parts of the world. In India, for example, you may have organic waste. For example, certainly found when we're doing research in Ecuador, a lot more organic waste than we get in the UK. It also changes at different times of the year. In the summer, we have summer here. There's a lot of garden waste gets produced, which adds to the organic part of it. We're probably seeing less paper now as people getting less, or so fewer newspapers being sold. And again, at different times of year, you might find more waste of different categories as well. And what organic fraction also varies in the diet, what people eat at different times of the year. But anyway, we're going really with the idea of a model for our waste fraction, and we need to then think about sensitivities and get the idea of what the ultimate analysis of this waste is as well. So I'm going to now run through different processes. And so this is our different stages. So we have the initial solid waste coming in. We've got 1,000 kilograms of this. These are our vertical process here of going from our waste coming in to our flue gas going out and electricity going out. And we've got chemicals which are being used in the processes. We've got ash being produced. We've got heat recovered. We've got air pollution control and flue gas. And we've got residue from air pollution control as well. And so that's what goes on. And from this model, and again, this is validated literature. We've got about 400. In our model, it's 428 kilowatt hours of electricity per ton of waste. And again, it would vary depending on waste mixture. But again, it's in line with what we found in the literature as well. We look at the general gasification route. So we're just using gasification to produce electricity. We have, again, various inputs into this. We get waste materials being recovered. We've got combustion, again, air and urea there. And we produce a little bit less electricity through gasification. And again, we've got the cleanup processes as well. So that's the gasification route. So we get a little bit less electricity from this route and a little bit more complicated. So again, not quite as economic. For methanol synthesis, so we have our miscible solid waste. Again, we've got a number of different compounds being used in the process to produce syngas. We get methanol being produced through the reaction tower, as we saw earlier. We've got some cleanup then of the methanol. So we have 86 kilograms of methanol being produced as a fuel, and then unreacted gases, we then produce about 233 kilowatt hours. And the conversion process is not particularly great, as you can see. So if we think about sort of the previously, so we're still getting about half of the methanol we get about half of the syngas still being converted to electricity. So the methanol process at this stage has some limitations. Then we've got our indirect dimethyl ether route. So again, we get to dimethyl ether, and again we get electricity produced because it's not a complete conversion process. Similarly, with the direct route, we get a bit more dimethyl ether, but we also get electricity being produced because we're not fully converting all the gas to dimethyl ether as a fuel. So we got a lot of unreacted gas still going through the process. Again, we can see what's in, and we've got our output as well here. Then for the solid oxide fuel cell, again, so we have our same start with the gasification process. We clean up the gas, so it can then be used in solid oxide fuel cell. And we produce more electricity because it's a non-thermal route. So with the combustion gasification, we generate a lot of heat from that, which is not tapped in terms of the efficiency of the steam and gas engines. So we produce more electricity, and then in unreacted gas, we can still produce some more electricity. So from a purpose of generating electricity, then solid oxide fuel cells seems to be a good route. And I think lastly, then the methane route, then. So again, we produce municipal solid waste, we make the syngas, we produce methane, and then we also have some electricity being produced as well. Okay, so that's our inventory approach. So this has been our life cycle inventory, so our second stage, and then we need to think about what happens to those. So these are what the actual impacts are going to be. And this is again an established methodology, and we made use here of Similar Pro software. And what we then look at the lifecycle impact results to see where they affect different parts of the environment and on people. So through the methodology, we can then assign the compounds which are being produced to different routes. So they are synergenic. Do they cause cancer? Are they affecting our respiration compounds? Is there any ionizing radiation or ozone depletion taking place? Then we can also think about the effects on the natural environment in terms of water, land impact, and water eutrophication as well. Global warming, of course, that's quite important these days. All days. So we think about what global potential going to be, and then also what resources have we used in these processes. So what's our use of non-renewable energy and also minerals? What are those resources going to be? So by separating those out, we bring them all together again to think about human health, ecology, environmental quality, climate change, and resources. So let's look at the results. Apologies, I am for the right-hand legend. The colours haven't quite matched up when I changed the template. But from left to right, combustion, the left, right. And so what we can see here is the effects on the endpoint and also on the midpoint categories. So for all these processes. So we can see here in terms of effects on health, some seem to have potential positives. So actually not causing effects that harm human health. Okay. In fact, gasification is seen to be the least harmed human health. Ecosystem quality, there's not a lot going on here, and you can see sort of in the middle here there's a real absence of effects on the ecosystems, but it's seen that methanation appears to have the sort of least impact and benefits to the ecosystems. For climate change, well, everything has an impact on the climate. Everything is considered to be negative. Well, I say, in terms of its effects on climate change, I think it has a positive effect, so which is what we don't want. And actually, the solid oxide fuel cell, which is the technology which has the least global warming potential. And when it comes to resources, there's not a lot of difference between many of them, but overall, the direct dimethyl ether program, in terms of non-renewable resources, has some great benefit. So from a resource point of view, you can see that. So you can see that there's no absolute winner to these processes, but if we look at a little bit more detail, we can see overall where the impacts are going to be. So for combustion, we can see its emissions are a problem. We get the benefits of electricity generation. For gasification, so again, if the emissions are a problem, and then benefit is electricity. We also get waste recovered with metals. For methanol synthesis, again you can see it's climate change emissions. We get benefits of electricity. We also get benefits of use of methanol as a fuel. And then we go through these emissions. Again, dimethyl ether. Same with the direct dimethyl ether production as well. We get the same things. And then the life cycle assessments for solid oxide fuel cells. So again, we have the emissions, but then we've got the benefits of having electricity being produced. And then the methanation, we get emissions, again, climate change, methane. So what we can then do is compare the different processes at their endpoints, and so this ranks them in order. So sometimes from a ranking you may hide the differences. So these are 1, 2, 3, 4. The difference between 1 and 2 may be very subtle, and I think that's definitely the case for the resources. There actually was a lot of difference in the resources. So again, these need interpretation. So if we look at these, then we can see that ranking first overall for human health gasification, methanation is good for the ecosystem. Global warming potential, best routed fuel cell, and resource consumption is the direct dimethyl ether synthesis. And ranked second, we've got gasification, and is good with human health systems, methanation, systems and warming, and then solid oxide fuel cell actually isn't reason it's not 1 and 2 well, because for global warming human health it's because of that's already been occupied as the first one, so 1 and 3 there overall. But generally overall, it's the solid oxide fuel cell which ranks the best overall. So from purely the life cycle assessment perspective, we can see that generating electricity through the solid oxide fuel cell has the least environmental harm out of all these technologies. As I said, that's great, but we have to think about the economics associated with this as well, which is why combustion is still being favoured, even though it's one of the worst overall. So if you think about looking at combustion, it's quite low with its 7s and a couple of the 6s, not quite as bad for human health. It's still not very good. Okay. Now, okay. So that's fine, but we can then think about could we actually make some improvements to our processes so we can make a decision. So okay, right, this is what we've got. Can we actually improve our processes even more to make things better? Now, the typical methanol yield associated with see how the ranking then forms by the increase of methanol production from 0.4 to 0.6. We can see that there are some shifts in the rank order. So we have methyl ether process increasing, it has some benefits, and that then reduces some of the other processes. So particularly here we see the difference between direct methyl ether, it improves its rank, and we get a reduction in the solid oxide fuel cell. So overall, by changing the process, we see that the direct dimethyl ether production actually would win out as being the best process. So that's just to get a little effects of what life cycle assessment do in terms of decision making, make you think about your processes, and then just ways to improve your activities, reduce your impact, and improve your production of your product. Okay. So we'll just now conclude this presentation now. So as you can see, the overall idea behind this was to look at life cycle assessment for range of different ways to convert municipal solid waste to electricity and chemicals. We started by looking at those mature technologies, those which could be developed into commercial systems, and looked at the range of different effects. Because it's a complex process, and you've got a range of different criteria, and so it appeared that for human health reasons, gasification you could choose. For the ecosystem, it would be methanation. For the climate change, solid oxide fuel cells, and resources, dimethyl ether through direct synthesis. So those are sort of conclusions. And overall, solid oxide fuel cells was the best route to take. But by looking at the sensitivity of, well, could we actually get more fuel being produced from the processes, we found that direct methyl ether would actually work out to be a preferred route. Okay. And so that's probably got to the point we want to sort of conclude, except to say that obviously you need to consider the sort of economics beyond this as well. It's fine to sort of look at this from a sort of a modelling perspective, and we need to then know would it actually work and make more money in practice. And so what's the value of the fuel producing more dimethyl ether as opposed to other routes? But what we can certainly see that from this particular process is that it does allow those comparisons to take place, and allows people then to make decisions based on these results and look in more detail. Okay. So I would just like to finish by with a couple of acknowledgements. This work was actually presented, or part of this work was presented at a conference on green process engineering, and my co-authors are Dr. Nanban Chimanan and Dr. Ramin Bayama, and some of this work was supported by the Ministry of Science and Technology from Thailand. And also I'd like to thank Anne Vika, who's a former student from Loughborough, he's actually from Nagaland, and he arranged a visit to the biscuit factory when I was in India a couple of years ago, and when I was able to visit him and the government in Nagaland. Okay, so I'd like to thank everybody very much for coming today. My last point just raised is I'm actually a guest editor for a special issue for a journal on bioenergy sustainability. So if you are interested in submitting an article to this journal, please make a note of this web link and my email address if you have. We've probably got time for a few questions now. But if you want to ever follow up afterwards, then feel free to do so. So I'd like to thank everybody for their attention. Thank you.
Thank you, sir. Now it's to the participants. If you have any questions, you can put.
Sir, we have actually I have been working in cogeneration thermal power plant, captive power plant. And we are having an agro-fired boiler. So in India, when we want to fire waste, municipal waste, organic waste, so here the laws are stringent. So what is the technology, electrostatic precipitator, or which type of technology for the flue gas are using in the country?
Yes, so that's a very good question, because that's the big part of all thermal processing is actually the treatment of the waste. So we will be making use of certainly electrostatic precipitators that are used for catching particulates. We also use activated carbon for capturing organics, and we'll be also using alkali to capture acidic emissions as well. Dust bags are used, so as in I suppose what you're trying to think like vacuum cleaner bags, large bags to capture large dust particles. Because again we are restricted as well in terms of emissions, so that you aren't allowed particulates to go out of the exhaust stack. And that's for all thermal plants, not just for electricity generation, cement industry as well. Is another example. So I think the best available technology is what we're using, and I think that's I guess that sounds like very much the same which you're using as well. So it is a requirement here too.
So in our case, now we were having electrostatic precipitator already in our boiler. So because of law, we are adding MDC, mechanical dust collector, before ESP. So whether it would be sufficient for having the SPM level dropping to the stringent level?
I think it's difficult to comment on the exact circumstances. But we have as I said, we have the large bag approach to actually capture large particulates. We have electrostatic data as well for smaller particulates. And also then to do with gas compounds which might be introduced, activated carbon and also alkali to deal with acids, sulfuric acid, hydrochloric acid. But so it's a bit difficult to comment on the precise system which you have.
Sir, in India, because now law is getting stringent, so having the systems like this in sequence to the exhaust and would be having a draft loss, means you have to have the more reduced draft fan capacity has to be increased further onward. So what can be the sequence best for the municipal solid waste in consideration of your country after a boiler outlet? What are the sequence of the equipment which you are telling should be there to go to chimney? Before that, what should be the sequence of the equipment? Like you are telling, what should be the sequence at first?
Right, let me find a slide. Hopefully I can show you. Where are we? Let me show you.
If you don't find the sequence, if you don't want to find the slide, don't worry. Just
I've got it now.
Speak out the sequence. That's all.
Yeah. Okay, can you see this one? Right, so this is a typical waste to energy plant. Can you see that okay?
Yeah.
Yeah, okay, so this is the boiler system in the middle here, the economizer. We then go through adding lime and carbon here. Okay, so that's to the acidity and also for the carbon. And then that goes into filters. Okay, so this is our filter process, and then that goes up to the flue gas. So that's our main route.
So fabric filter has to be provided. Fabric filter has to be provided.
Yeah. And this is in the middle of the city. Yeah. In Coventry. Yeah.
So you want to say after boiler outlet at first should be?
Well, the first stage treat the gases. So we
Okay.
treat the lime to get rid of the acidic gases, and we add carbon activated carbon to get rid of any organic things which might have formed, like furans and dioxins, which might have formed. It then go into the treatment stage, getting rid of the particulates, and then goes back out of a chimney area.
Thank you very much. Thank you.
You're welcome.
Hello, sir. Sudhir here from India. Hello, am I audible to you?
I can hear you, yes.
Sir, actually, I want to know what kind of mechanism do you use to segregate non-combustible material from MSW?
Okay. So the normal process is what we call separation. Okay. So what we've trained the British public to do is to try and sort their waste. So in the household level, we now have different bins. So I have, for example, a bin where I can put in my paper, cardboard, plastic and glass. Okay, and that gets collected day. And then my general waste. So that's stuff which is you can't recycle yet. So sometimes single-use plastics. Maybe some food wastes, maybe some contaminated mixed waste, dust, and things like that. So that's what we try to do is to separate things before they get to the waste plants. Now, as I said earlier, it's difficult to get everybody to do this. People live in different circumstances. If you're living in, for example, a tower building, it may be more difficult. So tower blocks, it might be difficult to separate your waste because of access to facilities. But what we try to do is separate the source. When it gets to the waste, which then comes to the municipal solid power stations, it's not separated. It is literally coming in. I'll show you this picture. This illustrates what takes place. So we have the lorries come up, they back up, they empty themselves out into this big pit, and it's all the waste, non-recycled waste goes in here. So this would include it can include bricks, garden waste, people who haven't recycled materials, so plastic, waste from commerce, metals, all sorts of materials just mixed together. So this is material which isn't separated. You don't do separation at this stage. We do it at the source, which is at home or at the company where they separate their waste, and that's what takes place. This is really just a stage of there's nothing more you can do with it. It's mixture. It's contaminated. So you can't recover anything from this, and that's then goes for combustion in this case.
Thank you, sir. Thank you. Sir, one more question can I ask?
Go for it. Yes, sure.
Sir, can refuse-derived fuel, RDF, be produced from the non-combustible, waste? Refuse-derived fuel, can it be produced from the non-combustible? Yes, sir.
Okay, here's what I had earlier. So non-combustible material is removed. Okay. And then you have whatever is potentially combustible. So plastics, paper, wood, that sort of material which goes into the RDF.
Okay.
Yeah, so it has to be treated to remove non-combustibles.
Okay, sir. Got it. Thank you very much.
Okay, you're welcome.
So, what are the chances of any, the person who want to destroy the plant where the municipal solid waste is being fired? So, whether can any explosive or any sort of thing can be segregated from the total fuel refuse?
No, I mean, I think whatever comes into the plant will go through it. This is the plant itself at Coventry. And talking of the operators, sometimes get issues where you have. They had an instance where someone had put in a large plastic bin. So if, I don't know how it is. In commercial waste bins, much bigger than household bins, sort of things, four wheels. I don't know, 2 or 3 meters by 2 meters by meter, maybe a meter and a half tall. And one of those was put inside the waste, and it was also full of plastic. And what happened is that the grab. So this grab here, it can pick up about a ton of waste at a time, and it picked up this, not seeing it, and it put it into the boiler. So it dropped it in here, and it just caused problems. There's so much energy wasn't expected, and caused system to overheat because you got this. So you don't necessarily need destructive activities like explosives, but even waste itself not mixed up, then you can get problems of causing damage. And these systems they need to they take days to cool down. And the problems with producing waste time. So that's why at Coventry they've got 3 of these combustion systems. 2 are used all the time. The third one is on standby. Should the other two not be able to work, or they need to close it for maintenance. So you can get problems. But generally plants can operate effectively with whatever goes in. But so you can get things going. Gas cylinders, for example, could get inside. So again, if someone put in a propane cylinder inside one of these, that could cause problems. So, but it's not always possible to find these in the waste, because even a small gas cylinder, a 35 litre gas cylinder, or a 15 litre gas cylinder, could get inside and still got gas in it, would probably explode. Or at least, the valve would probably go first, so wouldn't necessarily explode because the valve would go.
So what are the possibilities are there, because in India and around the world, municipal solid waste is accumulating. So what can be the possibilities with the proper technology? Why not worldwide this waste heat cannot be used, because municipal solid waste is accumulating still.
Yes.
Everywhere you are finding.
Absolutely. Thank you very much.
Sir, in addition to this, I would like to add, considering the clean and green environment that we are targeting, especially in India. So please highlight how this MSW is going to be an alternative for us.
Yeah, I think the first thing we should do is to think about why are we producing so much waste. So that's my sort of my question is, we all need to think about this, is why in the UK we individually it's about half a ton per person. In other places it's more. We did a study in Bahrain in the Middle East. It's 1 ton per person of waste being produced. So you have to think about that, and then you need to think about what are the state policies to actually deal with this. So different countries have got different priorities. We've got places which we're still seeing very little in the way of environmental legislation. We're also seeing places where there's more advanced stages of environmental legislation. With all these things, developing systems, come at a cost, and it ultimately what society wants, to do. So it's very much about what is it that society wants. Because even though energy is being gained from these processes, I'd probably say that the reason for doing waste to energy is to actually get rid of the waste. Okay, so you've got all this material being produced. So if you've got large amounts of waste being produced and slightly polluting waste, it's going to cause smells and water pollution, harm, disease, pests. You'll get with this. So the driver is to get rid of the waste, but it's not solving the problem. The problem is making waste. So there's all that idea of some utopian change of society whereas a lot of people haven't had the chance to have a good life. We need to think about how we can reduce the waste. So what we do in energy for waste is we reduce the volume of waste by 9%. So through the combustion of waste over time, we reduce the volume just by burning it by 90%. And we capture the energy from this, but it means we have a much smaller amount of material to deal with. And you can, the bottom ash material, let's see the picture here, we've got, so you can produce, this is what's coming out of a power waste to energy plant. So it's lots of soil and dust and brick material plus the metal recovered in here. It can be then segregated, and you can use some of this bottom ash building material. So you can have other things. So it's a good way of reducing the volume and actually then making some material from it. But you've got to have policies in place and systems in place. So you have to collect waste. So you have to have collection facilities to collect the waste, and it's got to be paid for. So people have to be willing to pay for the waste to be collected. And that's really the route to trying to improve the environment. But the disadvantage, I think you might have seen from the slide is the global warming impacts. That it's not a carbon technology. So I've got close the slide. I think so. Let me. So you see, the climate change impact quite high with example solid fuel cells, and it's not as bad as coal combustion. So greenhouse gas emissions are not as bad as coal. But they are worse than gas generation. So combustion process is not a low obvious still produces greenhouse gases. And so we then think about how can we reduce these greenhouse gases? Is it carbon storage? Are we plant up forests? What is it that we actually need to do? So it comes this process of life cycle assessment complex. Then when you start to build in the politics and the laws and the economics and what people want, it then becomes quite complicated. I'll tell you, in this country, do not like waste to energy plants generally. We have one being built very nearby, within about a mile of my home, and people think they're not very good. So even though they're dealing with the problem people make, people don't like them, and it's a that's the sort of a challenge. It's a necessary requirement to treat with waste, but it does mean we have to think about the consequences of what it has, the effects it has on people, and then also what it has in terms of particularly global warming. So I personally think something is needed, but I would really love it if we didn't need it. Thank you.
So thank you, sir. Thank you for inviting us.
Thank you very much.
Yeah. We hope to meet you again. Thank you. Thank you all the participants.
Thank you.
Thank you. Thank you everyone for attending. I hope the rest of it as well. It looks a very interesting program. There's some very good talks which you've got from colleagues in India. So I hope the rest of the course goes very well. Thank you very much for the opportunity.
We have learned a lot. Thank you.
Thank you.
Thank you, sir. Thank you, sir.
Okay, thank you very much. Bye everybody. Okay.
So this is the end of our today's session. So tomorrow we'll again meet at 10 o'clock in the morning. So the schedule has already been shared. In past sessions, we have Dr. P.M.B. Subbarao from IIT Delhi. Next, Dr. Sandeep Kumar from IIT Bombay. And after lunch, we are having Dr. B. Ashok from IIT Delhi. And at last, we'll be having just a little bit change, Dr. S.S. Ramadasi from ARAI Pune. So that's all for today. Thank you.